100 years of quantum, awakening industry. This is the theme of the conference today. This is a really great theme for the conference because today, right now, 100 years into the quantum revolution, it really feels that there is an awakening of an industry that aims to utilize quantum at a whole new level and put it to a good use. Today, the quantum computing industry has reached a point where many players, many very serious players, like Google and AWS and IBM, many other serious companies, many very well-funded startups with very deep expertise, are seriously and actually very aggressively targeting the building of a fault-tolerant quantum computer with thousands of logical qubits. That's where we are today. At Quantum Machines, we develop and we build the classical side of a quantum computer. So the quantum computer has two parts, the quantum hardware. That's where the magic happens. That's where we have the qubits and the entanglement. And that's where the quantum computation happens. But then there is also the classical side of the quantum computer, what we typically call the control system, that needs to control, communicate with the quantum hardware, and operate it. So the biggest challenge in building a fault-tolerant quantum computer is actually on the quantum side. It's to build better qubits and scale up the quantum processor. That's the hardest thing. But there are also extreme challenges on the classical side if we want to scale up quantum computers and bring them to fault-tolerant quantum computing. So today, I want to tell you a little bit of what are those challenges on the classical side, what needs to be done on the classical side of the quantum computer in order to reach fault-tolerant quantum computing. And I want to tell you a little bit about what we at Quantum Machines are doing to push this forward. So at Quantum Machines, we divide this to three different challenges. We have the feed-forward and real-time decoding, which also Professor Kim talked about it a lot in the keynote speech this morning. Then we have the low physical error rate challenge, and finally scaling. So I want to talk about each and every one of them and tell you about what we do at Quantum Machines on these fronts. So starting from feed-forward and real-time decoding, Quantum Machines, the roots of our company are actually very deep in quantum error correction. My co-founder, Nissim Ofek, was the first to actually demonstrate quantum error correction for real in his postdoc at Yale University with Professor Rob Shulkoff. This is a Nature paper from 2016, which is called Extending the Lifetime of a Quantum Bit with Error Correction and Superconducting Circuits. That's the first time that someone showed that you can actually extend the lifetime of a qubit using active error correction. But actually, even though, Nissi, my co-founder, did this first quantum error correction experiment, a few years ago, we realized that we still don't fully understand the requirements from the control system, what is needed from the control system in order to do quantum error correction at scale and reach fault tolerance. So we decided to do our own research on the topic, and this work from Yaniv Kuhlman on our team, which is the second paper we published on this topic. What we do here is we took an application, Shor's algorithm, to factorize the number 21. This is the circuit that you see here at the logical level. And we broke it down to its very pieces to understand what is needed to run this system. So what you see in the bottom figure is how we break down a single logical operation down to the surface level implementation. But what we did in this work, we didn't just break it down to the quantum operations, which you see here. We also looked at the classical operations, and also how the classical and quantum connect. So this orange line here is the feed-forward operation. This operation on the right side is the dependent operation or the conditional operation, and it depends on the left, on the measurement here, the ZZ measurement. Okay? But it doesn't actually depend only on this ZZ measurement, it depends on the decoding of all of the error syndromes coming from these two surfaces here, actually from the last feed-forward measurement. So that's very in line with what Professor Kim talked about. So you can do this to the entire circuit. You can look at all the quantum operations, all the surface operations, but also all the classical operations, all these decoding tasks that we show here in different colors, and then also the feed-forward operations, all of these orange wiggly lines here. And when you do this, you can learn a lot, actually. First, you can see that those feed-forward operations can be delayed. You don't have to do them right away after the last measurement on which they depend. You can delay them further into the circuit, playing all kinds of tricks. The other thing is there is this complicated workflow of decoding tasks. This is what you see also in the bottom figure here. These are all the decoding tasks and their dependencies. So there's this workflow of decoding tasks that need to run, some of them in parallel, some of them have dependencies. They also depend on communicating with the control system to get all of the syndromes from the right qubits. And we cannot even predict in advance what will be the timing of this decoding task because they depend on the errors themselves. Okay, so we cannot predict timing fully in the circuit. So we did this work, and you can extract many different requirements from this. So I won't go over all of them, but the main thing that I want to focus on was what we were really after, which is what is the needed latency for these feed-forward operations. And we took the fastest implementations of quantum computers that there are out there, such as the Google architecture with transmons. These are the most demanding in terms of feed-forward latency. And you can see that you need about 10 microseconds of decoding latency or feed-forward latency, even for the fastest implementations. This it was very important work for us because it led to the development of a new product, a new architecture, which we worked on together with NVIDIA, which is called this GGX Quantum. And that's the first of its kind of architecture that connects the control system with the NVIDIA GPU, CPU system with very, very low latency. So what you see here is that we connect our control system that's connected to the qubits to the server with the GPU, CPU system inside using this OpenNIC, this network interface card, which is a PCIe-based card. And that allows us to reach less than 4 microseconds of round-trip latency, which is the first time that something like that is done. And it's very important that we also did the research into the requirement because we can build systems that are based on standard hardware, standard software that can reach these latencies. This system is fully software programmable. It has also a very wide bandwidth of communication, and it really meets the requirements that we could figure out for quantum error correction. Next, it's not enough to just do one connection between a controller and a decoder. You also have to scale it up. So as we saw, you need these many decoding tasks. They need to be parallelized. They need to communicate with many different decoders. So we actually defined a whole architecture for what we call the quantum control or quantum error correction data center, where we have these control units, and they are connected to these quantum error correction acceleration servers. Each can host different types of decoders, CPU, GPUs, and also other types of resources like FPGAs, ASICs. And you can connect these through this low latency network that I mentioned, this network interface card, to scale it up and have a full data center which is dedicated for quantum error correction and can reach those latencies that we just saw are needed. We also discussed this in more detail in the recent position paper that we wrote with our consortium with HPE, NVIDIA, Colab, Applied Materials, 1QBit Synopsys, and many other players in this consortium. Okay, so this is about quantum error correction. The next big challenge on the classical side of a fault-tolerant quantum computer is low physical error rates. So I want to go back actually to this slide about quantum error correction and show maybe the most important requirement for quantum error correction is that we don't start to do quantum error correction if we don't have low enough physical error rates. If we don't have low enough physical error rates, it's very, very hard to even start thinking about quantum error correction. So in this work, we took the assumption that the error rates will be down to the 0.1%, which is what the biggest and most leading players are targeting these days. But if you want to reach this, so of course, again, you have to build better qubits. This is the hardest part. But also, you cannot have the control system limit the fidelities of the quantum operations. So there are two parts to it. There is the analog specifications of the hardware, how pure are the signals, how accurate they are, what's the noise level that we introduce into the quantum system from the control system. And the second thing is calibrations. We constantly need to calibrate and optimize the performance of the computer using sophisticated classical control techniques. Here again, I just want to give you a few examples of how we look at this at quantum machines. So looking at a superconducting-based system, we typically want to control these devices that have qubits and couplers. And we have two types of control channels that we use to control these, the microwave signals and the baseband signals. And both of them can affect both qubit coherence and gate fidelity. So there are many different analog specifications of the control hardware, but I want to give you some examples just to give you a taste of how we view this problem and how we analyze these problems. So one of the ways, for example, in which the microwave signals can affect qubit coherence is by introducing noise into the readout resonators that we use to read out our qubits. So even if you inject the lowest possible noise from room temperature, which is minus 174 dBm per hertz, that's the thermal 50 ohm resistance noise level. Even if you introduce that low noise into the fridge, still it could populate the resonator with photons and decohere your qubits. So we have to put a lot of attenuation in the fridge to attenuate the signal if we want to reach more than 1 millisecond of coherence times for these types of superconducting qubit devices. This in turn tells us what is the level of signal that we need to introduce into the fridge, because we want to read out fast and we want to read out with high fidelity, so we need to send very strong signals into the fridge. And now we have this attenuation, so we need that defines the signal level that we need. So that in turn gives us the signal to noise ratio that we need in our control system. And that's the kind of analysis that we do to define the specifications of our control system. So OPX 1000, which is our flagship control product, was designed with this in mind. Here you can see the SNR of the OPX 1000, which is actually thanks to the direct digital synthesis technology that we're using, DDS technology, we're able to reach above, actually better than 150 dB of SNR in most of the spectrum here. Okay, in the same way, you can look at how the microwave affects 2-qubit gates. This is an example from a particular 2-qubit gate called iSwap gate. We want to reach 10 to the minus 4 error rate, as we discussed. But the problem is that these gates are very sensitive to the phase drifts between different channels in your system. So here is a curve that shows how the gate fidelity would be affected by the phase drift in the system. And so we analyze this, and we find that in order to be below our 10 to the minus 4 threshold for these 2-qubit gate errors, we need to have phase stability of the control system of better than 14 millirads during very long time periods. Again, this is how we define the specification of the control system of the OPX 1000, and we're able to do that. We're able to reach very low phase noise and very low long-term phase drifts that bring us to the specs. Very importantly also, when we scale this up, we believe that it's not enough to just build very stable electronics. You also need active methods to stabilize the system. So, as I mentioned, our OPX 1000 can do these feed-forward operations, both for correcting quantum errors, but also for correcting classical errors, in the sense that we can measure those drifts, what we call in situ or embedded. We call it embedded calibrations. We measure very fast those drifts, and we can, within the controller, change the phases of the control system to flatten this phase drift curve. And we believe that these kind of embedded calibrations are going to be very important going forward in the field. And in the same way, you can look at the baseband signals and how they affect the qubit coherence and the gate fidelities. Here, I won't show the analysis, but we, again, see that we need very low noise, voltage noise for these signals, below 1 ppm at 1 hertz, assuming 1/f spectrum. And at OPX 1000 does better than that. And again, here I also think that we will have to find ways to stabilize a very large system in situ in an active manner. This is work that we're also doing these days very tightly in collaboration with Colab, the new startup by John Martinez, who led the development at Google for many years. And we're collaborating to build such electronics and stabilize the system. Okay, so that's about the hardware, okay, and how we think about the specification. But as I mentioned, there is also the issue of not just of analog specifications, but of calibrations. So recently, we came out with a new product that we called Qualibrate. This is open source software for calibrations of QPUs at scale, to automate the calibrations, to create those graph-based calibrations and automate them. I won't go into the details of this software. There's a lot to discuss on how to build such software in the right way. But one of the things that I would just mention that the thing that was most important for us, I'd say two things. One is to build a very modular software so that people can use not everything but bits and pieces of it and connect them in different ways. And the second thing is that this is open source software. Okay, we are already collaborating with the community on this development. It's not just developed by Quantum Machines. And we believe that that's very important because we need this infrastructure for calibrations to be very open and very collaborative and build open source software on which people can build their own solutions. So these are just some of the testimonials from the very first users of this. So we have Simon from Oxford Quantum Circuits. We actually used Qualibrate to bring up Oxford Quantum Circuit device in less than 2 weeks and reach results that are on par with the state of the art that was done in Oxford Quantum Circuits. Great QPUs. This is by Izhar Medalsi from Quantum Elements. So these are software companies that are building actually on top of Qualibrates their proprietary solutions. In this case, quantum simulators that can be added on to our open source software to create digital twins of the customer system. And finally, from John Martinez, again, who led the development at Google, who performed John led the quantum supremacy experiment, and today his company are using Qualibrate very extensively, actually, to calibrate their new devices. Besides the software that we need for automating calibration workflows, again, we need the hardware systems, the underlying systems that will allow us to do it very fast. Here again, we believe that DGX Quantum is going to play an important role, so not just for quantum error correction, but also to run these neural network reinforcement learning-based calibrations that, again, I believe that are going to become in situ, embedded in the system. Eventually, we need them to run very fast in a way that's transparent to the user. So this is work that we did, again, of course, with NVIDIA and also Rigetti at the Israeli Quantum Computing Center, where we calibrated, optimized quantum gates using reinforcement learning agents that we put on the Grace Hopper system in the server here, and with a closed loop between the controller and the Grace Hopper. Okay, so this was the second challenge of low physical error rates, at least on the classical side. Again, we need the qubits to be also very good for that to work. And the last thing is scaling. So scaling, I'll just sort of give a spoiler before I even dive into the details. For us at Quantum Machines, scaling the control system is all about developing ASICs. We believe that CMOS technology can provide us everything we need to really scale up the control system very, very significantly. What needs to be done is we need to lower the cost per qubit control, because the cost of qubit control today doesn't scale. We need to really lower it significantly by orders of magnitude. We need to lower in the same manner the power consumption per qubit control. And finally, the size. So we need to also densify the system. So density, power, and cost are the key things, but we know how to do it by moving from FPGA control-based systems and not dedicated chips for control to dedicated ASICs that we plan to develop. I want to show you how we've already done some things in that respect and how significant it is even before developing a full-fledged ASIC for quantum control. So this started about 5 years ago. We started looking into a new technology called direct digital synthesis, or DDS, where you generate you generate the microwave signals in the digital domain instead of in the analog domain. So in these two top figures, you see how people used to do it with external mixers, and this has been the way that people worked with, for years. And this is okay. There are many ways to do it, but eventually, when you move to generating everything in the digital domain in your CMOS device, things change completely. First of all, the analog specifications improve dramatically, whether it's linearity, signal to noise, SFDR, phase stability, and other specs. Second is just the sheer number of elements here, as you can see from the figure. So you can really start scaling up, lower the costs, scaling the size, reducing the size, and the power consumption goes down dramatically. And finally, we discussed phase coherence. So here it's important to understand that working with these mixers, you have to distribute many different local oscillators and provide clocks to them, and this is a very complicated architecture. But with DDS technology, we can actually distribute a higher frequency clock and remove all of these phase locked loops, and this becomes a much simpler architecture to scale up. So, so this is just by moving some elements to silicon, okay? Not yet making a full dedicated chip. So and already we see a huge dramatic difference. We scaled up the density by a factor of more than 10, and the power consumption and the cost already dramatically. So we think that by going full ASIC, there is a lot that we can do. You also get a lot of digital features that you can use. For example, we widen the spectrum of frequency multiplexing that one can use, because we're doing all of this up conversion at the digital domain. So this allows us to create very far away tones. As you can see in this figure, all of these different tones are played from a single channel, and they're very far apart. It can be gigahertz, a few gigahertz apart. And that you can do thanks to, again, DDS technology, moving things to ASIC. So we're going to do it much more aggressively going forward. We started with OPX 1000 and DDS technology, which we're currently at, which can give a solution up to about 1,000 qubits. In our next step, OPX 10,000 and then OPX 100,000 will be based on dedicated ASICs that we're going to develop. We have the right team for that and the right resources for that. So at Quantum Machines, we recently fundraised. We raised $170 million just a few months ago, which gives us the resources that we need to go very strongly and very bullishly towards these developments. And we have a team that comes from ASIC developments, including many of our investors, and today, actually, many of our employees, which come from companies like Mellanox, Annapurna Labs, and others that know how to build those chips. This is not an easy task. You make one mistake, you pay a year of development, so you need to bring the right expertise for that, and I think we're pretty set up for success in this respect. With that, I want to thank you, and let me take some questions.